Future trends and innovations. The semiconductor market is projected to reach a staggering $1.2 trillion by 2030, driven by a compound annual growth rate of 12.5%. This growth is significantly influenced by artificial intelligence, which is expected to boost efficiency by 35%. A key driver behind this expansion is the widespread adoption of 5G and Internet of Things technologies, which require advanced, reliable, and energy-efficient semiconductor solutions. These trends are reshaping the entire ecosystem, supporting next-generation oxidation processes. The emerging tech ecosystem includes four critical pillars: automation to streamline manufacturing, machine learning vision for process monitoring and analytics, edge computing to enhance localized data processing, and security to safeguard the integrity of highly sensitive data. Together, they enable unprecedented control and flexibility. At the innovation frontier, atomic-level precision drives revolutionary impacts, improving process efficiency by 300%, reducing defects by 95%, cutting energy use by half, and shortening time to market by 40%. This is shaping the future of electronics. Semiconductor manufacturing. Semiconductors are at the heart of modern electronics. These tiny computer chips power our phones, laptops, and even vehicles, enabling everything from communication to automation. They are built on silicon wafers, thin, circular disks that serve as the foundation for billions of transistors. Each transistor functions like a miniature switch, forming the building blocks of logic and memory. These chips must be manufactured with incredible precision to ensure they perform reliably at high speed. The chip manufacturing process involves multiple complex steps. First, layers are built by adding thin films of materials onto the wafer. Next, patterns are etched into these layers to define circuit pathways by removing unwanted material. Cleaning follows, where all contamination must be eliminated to prevent defects. Finally, the entire sequence is repeated over 100 times to form intricate 3D structures. Because features are 1,000 times thinner than human hair, even microscopic errors or particles can destroy an entire chip. Key insight in semiconductor manufacturing. One of the most critical insights in semiconductor fabrication is the sheer frequency of etch and clean processes. On average, these steps are performed around 200 times throughout a single chip's manufacturing cycle. This makes etching and cleaning the most frequently repeated operations in the entire semiconductor process flow. These steps are not just repetitive, they are foundational. Each etch defines precise circuit patterns by selectively removing material, while each clean step removes microscopic contaminants that could lead to defects or failures in performance. Given how delicate and precise semiconductor features are, often just nanometers wide, any leftover residue or particle can compromise yield. That's why these two processes must be executed consistently and flawlessly. Their importance cannot be overstated. They are the backbone of maintaining pattern fidelity and ensuring device reliability in high-volume advanced chip production. Etching processes. Etching is a fundamental step in semiconductor manufacturing that enables precise material removal to define intricate circuit patterns. It involves the selective removal of specific layers from a silicon wafer while protecting desired regions. This process is essential for creating functional device structures without damaging the areas meant to remain intact. Etching achieves pattern creation by carving out circuit pathways and component shapes in multiple layers of material. The process operates with microscopic precision, often achieving features smaller than 5 nanometers. This level of control is crucial for modern chips, where size and performance are tightly linked. In the illustration shown, the layered materials before etching are uniformly stacked. After etching, only the intended patterns remain, leaving behind well-defined structures. Etching has widespread applications, including forming circuit pathways, opening contact holes, shaping transistor gates, and defining memory structures. It plays a critical role in building the microscopic architecture inside every chip. Etching processes, wet versus dry. In semiconductor manufacturing, Etching is achieved through two primary methods: wet etching and dry etching. Each has distinct advantages and limitations that make it suitable for specific applications. Wet etching uses chemical liquid solutions to remove materials. It's fast, cost-effective, and offers high selectivity, making it excellent for removing large material areas or cleaning surfaces. However, it etches in all directions, called isotropic etching, which leads to poor precision and limits its effectiveness for small, intricate features. Dry etching, on the other hand, utilizes plasma and reactive gases. It's directional or anisotropic, enabling sharp, well-defined structures at the nanometer scale. It allows for high precision and supports the creation of complex patterns essential in modern chip designs. However, dry etching is more complex, slower, and costlier compared to wet etching. Due to its precision, dry etching is preferred for modern chips and is essential for fabricating nanoscale features in advanced semiconductor devices. Types of etching techniques. Etching is a critical step in semiconductor manufacturing, where material is selectively removed to form precise patterns on the wafer. There are two main types of etching techniques: wet etching and dry etching. This presentation focuses on a detailed comparison between the two, beginning with wet etching. Wet etching is a chemical solution-based process in which a chemical reaction dissolves the target material into a liquid solution. Its etch profile is isotropic, meaning the material is etched uniformly in all directions, which can lead to undercutting beneath masks. Common chemistries used include hydrofluoric acid, HF, for etching silicon dioxide, SiO2, phosphoric acid, H3PO4, for aluminum, potassium hydroxide, KOH, for silicon, and nitric acid, HNO3, for metals. Wet etching is known for its fast etch rate and high selectivity, but suffers from low precision due to its isotropic nature. These traits make it suitable for some applications, but limiting for others where fine patterning is needed. Dry etching. Dry etching is a plasma and gas phase process that utilizes a combination of chemical reactions and physical ion bombardment to remove material from the wafer surface. The mechanism involves the creation of reactive species through plasma, which chemically reacts with the target material, while simultaneously, ions physically bombard the surface to enhance etching directionality. Unlike wet etching, dry etching features an anisotropic profile, meaning etching occurs directionally, which is essential for creating precise and vertical sidewalls in semiconductor structures. Plasma chemistries vary depending on the target material. For example, CF4 and BCl3 are commonly used to etch silicon, CHF3 is used for silicon dioxide, and Cl2 is used for metal etching. Dry etching provides controlled etch rates, tunable selectivity between materials, and ultra-high precision. These advantages make it ideal for advanced semiconductor devices where exact pattern fidelity and fine feature resolution are required. Etching parameters, technology nodes, and applications. Understanding etching techniques requires examining key process parameters, technology scaling, and application contexts. For dry etching, typical temperatures range from 20 to 80 degrees Celsius, pressures span 1 to 100 millitorr, and plasma systems operate at powers between 100 and 3,000 watts. Gas flow rates vary from 10 to 500 SCCM depending on the etching chemistry and desired selectivity. In terms of technology nodes, wet etching is viable for older, larger nodes above 100 nanometers. Between 150 nanometers, there is mixed use of wet and dry etching. As we approach smaller nodes between 50 and 10 nanometers, dry etching becomes dominant, and below 10 nanometers, only dry etching is feasible due to the need for precision and directionality. Applications also differ. Wet etching is common in microelectromechanical systems, bulk micromachining, and surface cleaning. Dry etching dominates in logic circuits, memory devices, and advanced packaging. Today, 95% of all etching processes in semiconductor manufacturing are dry etching. Cleaning processes. Cleaning is one of the most frequent and critical steps in semiconductor fabrication. The goal is to remove all forms of contamination to ensure chip quality and long-term reliability. Even a single microscopic particle can destroy an entire circuit, making cleaning essential. At the nanometer scale, where features are 1,000 times smaller than a human hair, contaminants like dust or debris can cause catastrophic yield loss. Cleaning protects yield and prevents billions of dollars in lost production. Various types of contamination must be addressed. These include particles like dust and flakes, chemical residues from previous processes, metallic ions, organic compounds such as carbon-based contaminants, and native oxide layers that form on surfaces. Because contamination can occur at any stage, wafers are cleaned over 200 times throughout fabrication. Cleaning occurs before every major process, after etching, before deposition, and at key checkpoints to ensure the wafer remains defect-free and fully processable. Wet and dry cleaning processes. Cleaning in semiconductor manufacturing is divided into wet and dry approaches. Wet cleaning relies on chemical solutions and ultra-pure water to eliminate contamination. Common methods include the dipping process, where wafers are immersed in chemical baths; spray cleaning, which uses high-purity chemical sprays to dislodge particles; and megasonic cleaning, which employs high-frequency sound waves to remove fine debris without damaging structures. Wet cleaning is effective for removing particles, organic residues, and metallic contaminants. On the other hand, dry cleaning involves plasma and gas phase processes. Plasma cleaning uses ionized gases to remove contaminants and activate surfaces. UV ozone cleaning breaks down organic materials using light-induced oxidation. Vapor cleaning uses gaseous chemicals to remove residues without liquid contact. Dry cleaning offers key advantages. It produces no liquid waste, allows precise control of surface treatment, and can activate surfaces for better adhesion or processing. This versatility makes it essential for advanced nodes and delicate wafer surfaces. Equipment and process control. Sophisticated manufacturing in the semiconductor industry demands equally advanced equipment and precise process control. Etch equipment includes plasma reactors such as RIE, ICP, and CCP systems. These are essential for defining intricate patterns on wafers. Wet benches, which utilize chemical baths and spray systems, handle delicate wafer etching with precision. Advanced systems like atomic layer etching offer nanoscale control, enabling the finest pattern fidelity. Tool costs in this category range from $2 to $15 million, reflecting their complexity and critical role. Clean equipment ensures particle-free surfaces. Wet stations process wafers individually or in batches. Dry clean tools like plasma and UV ozone units remove microscopic residues. Megasonic cleaning uses ultrasonic waves in liquid baths to dislodge particles. Each tool costs between $1 and $8 million. Automation enhances efficiency with robotic wafer handling, real-time control systems, and AI-driven predictive maintenance. The result is an impressive 99.9% automation level. Real-time monitoring and quality control. Maintaining optimal process control in semiconductor manufacturing requires real-time monitoring at an extremely fine level of precision. Tools are equipped with over 1,000 sensors, enabling continuous oversight of critical parameters. Temperature is monitored to within plus or minus 0.1 degrees Celsius, ensuring thermal stability throughout the process. Gas flow is controlled to plus or minus 1 standard cubic centimeter per minute, preserving gas chemistry accuracy. Pressure regulation is equally tight, maintained within plus or minus 0.01 torr to support vacuum-dependent operations. Power levels are also held within plus or minus 1 watt, which is vital for consistent energy delivery in plasma systems and heaters. In parallel, quality control is enforced through in-situ monitoring systems. These include optical sensors, mass spectrometry, plasma diagnostics, and electrical signal analysis. All are integrated into metrology systems that offer continuous feedback loops. This integration of metrology enables early detection of deviations, ensuring that every wafer meets the stringent quality specifications required for advanced semiconductor devices. Industry 4.0 integration. Modern semiconductor manufacturing is increasingly shaped by Industry 4.0 technologies, which drive intelligent automation and hyper-precise process control. AI and machine learning are central to this evolution. These systems perform predictive analytics to foresee failures, optimize processes for maximum efficiency, and detect faults before they disrupt production. This results in consistent, reliable manufacturing outcomes. Cloud connectivity enables remote monitoring of tools and factories, facilitating global coordination and access to real-time data analytics from anywhere. Engineers can make data-driven decisions without being physically present at the fab. Digital twins take this further by creating virtual models of tools and processes. These models simulate real-world performance, allowing for predictive maintenance and process optimization in advance of physical issues. Big data completes the ecosystem by compiling vast amounts of process history, terabytes generated daily. Pattern recognition algorithms analyze this data to identify trends and enhance yield. The outcome: 24/7 monitoring, plus or minus 0.1% process control accuracy, and globally optimized semiconductor production. Applications and industry impact. Semiconductor technologies power the digital backbone of modern society, enabling innovation across multiple trillion-dollar industries. In consumer tech, semiconductors are foundational to smartphones, laptops, gaming systems, and wearable devices. These chips drive performance, connectivity, and user experience, fueling global demand. In the automotive sector, semiconductors are embedded in electronic control unit, ECU systems, and support advanced driver assistance systems, ADAS. They also manage energy in electric vehicle, EV batteries, and power various automotive sensors critical to safety, efficiency, and automation. Data centers rely heavily on semiconductors, especially for AI chips, CPUs, memory modules, and high-speed networking components. These elements ensure high-performance computing, efficient data storage, and rapid data transfer for cloud services and artificial intelligence. In IoT and medical fields, chips power implants, enable diagnostic technologies, and support smart sensors. Edge computing further extends processing to the point of data generation, bringing intelligence directly into the device and enabling real-time responses in critical healthcare and IoT environments. Global impact and tech drivers. The semiconductor industry is a cornerstone of the global economy, reaching a market size of $574 billion in 2023. These advanced chips are embedded in nearly every modern electronic system. However, with that growth comes significant operational costs. 25% of total annual expenditures are tied directly to manufacturing processes. This drives the need for continuous innovation and efficiency in production. Key technologies enabling this industry include cutting-edge 3-nanometer process nodes, which deliver exceptional performance and energy efficiency. The AI revolution is accelerating demand for smarter, faster chips, while 5G networks push for lower latency and higher bandwidth. Cloud computing, meanwhile, requires robust and scalable semiconductor infrastructure to support global digital services. To meet industry demands, manufacturers must achieve a 99.9% yield across more than 200 intricate process steps. Every step must be tightly controlled to avoid defects, ensuring that only flawless devices make it to market. Precision, innovation, and global coordination define the path forward. Applications and industry impact. The semiconductor value chain includes several major segments, each playing a vital role in enabling chip production and system-level innovation. Starting with materials, chemicals and gases used in etch and clean processes represent a $50 billion market. These are essential for preparing and treating wafer surfaces. Next is equipment, specifically etch and clean tools, valued at $80 billion. These tools perform critical pattern transfer and post-process cleaning steps that directly affect yield and performance. Fabrication, the core of chip manufacturing is a $400 billion industry, entirely dependent on effective etch and clean steps to produce functional semiconductor structures. Products are, or finished semiconductor devices, form a $574 billion market, supplying components to diverse sectors. Finally, systems, which include all end-user applications like smartphones and data centers, exceed $3 trillion in value. Importantly, without etch and clean technologies, zero chips can be produced, halting the entire value chain. Challenges and future trends. The semiconductor industry faces complex challenges and future demands driven by technology, cost, and environmental responsibility. From a technical standpoint, sub-3 nanometer scaling pushes the limits of atomic precision, demanding extreme accuracy in patterning and material removal. The rise of 3D structures, such as FinFETs and gate-all-around transistors, introduces intricate geometries that require advanced etch and clean processes. Introducing new materials with novel chemistries adds to process complexity, while achieving extreme selectivity, with ratios like 1,000 to 1, requires groundbreaking innovation. On the economic side, the average cost of a new fabrication facility has reached $20 billion. Key cost drivers include equipment at 70%, materials at 20%, and R&D at 10%. Finally, sustainability is a growing concern. Reducing and recycling chemical waste, addressing the fact that fabs consume 50% of their energy on processing, managing water consumption in the millions of gallons per day, and responding to PFAS concerns with safer alternatives are all critical for long-term success. Breakthrough tech and AI revolution. Next-generation manufacturing is being shaped by both technological breakthroughs and artificial intelligence. Under breakthrough tech, innovations such as atomic layer etch provide monolayer precision for nanoscale structures, critical for advanced nodes. Plasma-free clean techniques offer gentle surface treatments, reducing damage to sensitive layers. Quantum dots support self-limiting etch processes, enabling ultra-fine control in nanofabrication. Cryoprocessing introduces ultra-low temperature techniques that minimize material damage and enhance selectivity. Laser etch, driven by photonic activation, allows highly localized and rapid material removal. Biocompatible materials promote green chemistry solutions, aligning with sustainability goals. On the AI revolution side, smart manufacturing relies on autonomous systems that are self-tuning, predictive, adaptive, and continuously learning. These systems improve process control and reduce human error. As a result, the smart outcomes are impressive: up to 90% defect reduction, 40% efficiency gains, and 30% in cost savings. Together, these technologies define the future of semiconductor innovation. Technology roadmap. The future of etch and clean is guided by a dynamic technology roadmap focused on achieving greater precision, intelligence, and sustainability. In 2024, the current state of the industry is defined by 3 nanometer production, the use of EUV lithography for extreme pattern resolution, and high-K materials that enable better electrical performance in advanced devices. Moving to 2027, near-term innovations include the transition to 2 nanometer nodes, the adoption of atomic layer etch for monolayer precision, and the integration of AI process control to enhance accuracy and reduce variation. By 2030, medium-term goals involve achieving 1.4 nanometer technology, leveraging quantum processing, and realizing zero-waste fabs for sustainable manufacturing. Looking ahead to 2035 and beyond, the long-term vision includes molecular etch for ultimate atomic control, biointegration to support new computing paradigms, and the emergence of autonomous fabs that run intelligently with minimal human intervention. This path reflects a shift towards smarter, cleaner, and more precise semiconductor production. Conclusion and future outlook. Semiconductors are the foundation of our digital future, and the importance of precision, technology enablement, and economic impact cannot be overstated. In manufacturing, precision is everything. Devices are built at the nanometer scale, requiring incredible accuracy in every step of etch and clean. To remain competitive, fabs must achieve 99.9% plus yield, leaving zero tolerance for defects. Every layer and feature must be executed flawlessly to ensure performance and reliability. These technologies are also technology enablers, powering transformative applications like AI computing, 5G networks, autonomous vehicles, and the expanding Internet of Things. These advancements rely on high-performance chips produced through advanced etch and clean techniques. Economically, the semiconductor industry is an economic powerhouse, driving a $574 billion global market. With a 25% share of overall processing coming from etch and clean, this segment supports the creation of millions of jobs worldwide. This makes the sector essential to both innovation and global prosperity. Conclusion and future outlook. Etch and clean processes are not just steps in semiconductor manufacturing. They are foundational to modern life as we know it. Without these processes, we wouldn't have smartphones, the very devices that connect and inform us daily. There would be no computers, eliminating the backbone of business, education, and personal productivity. Without the internet, the global flow of information would be cut off, and ultimately, there would be no modern life, no digital services, no real-time communication, and no smart infrastructure. On the other hand, with Etch and Clean, we unlock the potential for digital transformation across every industry. These processes enable global connectivity, bringing people and systems together in ways that redefine collaboration and commerce. They drive innovation acceleration, allowing technologies to evolve at breakneck speed, and they open up future possibilities, laying the groundwork for the next generation of breakthroughs in AI, healthcare, energy, and beyond. Conclusion and future outlook. Looking ahead, several key trends will shape the evolution of etch and clean processes. First, smaller nodes, such as 2 nanometers and beyond, will demand ultra-precise patterning and cleaning. As features shrink, the margin for error disappears, requiring etch and clean processes to be more controlled than ever. Second, the rise of new materials, including advanced compounds and 2D materials like graphene, introduces fresh challenges for compatibility and precision. Third, AI-driven control is transforming semiconductor fabrication. Machine learning is being used to optimize etch rates, endpoint detection, and fault prediction, improving both yield and efficiency. Finally, sustainability is becoming central. There's a growing push for green chemistry solutions and waste reduction, which will shape process development in the coming years. The key insight remains simple yet powerful. Every chip in every device depends on etch and clean. These processes are not only essential, they are constantly evolving alongside technology.